Another integrated circuit that we're going to be concerned with for the case of logic and electrical engineering will be the multiplexers and demultiplexers. So to introduce this device, consider a device with inputs and a selector to determine which input is used. So in this case, we're going to have two inputs, I0 and I1, and an output, Y, and the selector, given by S. Now how this device is going to work is when S is equal to 0, it will select I0, and when S is equal to 1, it will select I1. So we can write a truth table in terms of S and Y, and this looks a little bit different to the truth tables that we're used to, because now where we have I0 or I1, these values could be zeros or ones. They can change to whatever they want. It's simply the selector pin that's going to select which output to use. And this is what we're going to call our multiplexer or MUX. But for the multiplexers, we're going to have a certain number of selectors, and those will select inputs, and the number of inputs is equal to 2 raised to the number of selectors. So for the case where we have 2 selectors, we would have 4 inputs. And now we can have a different truth table where we have S1 and S0, and then our output. Now we can have the opposite, where we have an input, and we can have 2 selectors, and based on the combination of the selectors, it will determine which output receives the input. This is what we call our demultiplexer or DEMUX. So we want to look at how we can implement multiplexers and demultiplexers into Boolean functions. To do that, we're going to consider a 3-input function, f as a function of w, x, and y, being equal to the min terms m3, m5, m6, and m7. So we have 4 inputs, 2 selectors. So we're going to have 4 individual cases. Now we want to group the truth table as follows. And what this does is allow us to look at w and x and see that for these subdivisions, what we get is w and x being equal in each grouping. And because we're looking at w and x, we're going to call these inputs w and x for the selectors. Now let's consider this first grouping here. So we know that w and x being equal to 0 will contribute to f being equal to 0. And we'll notice no matter what y is, f is always equal to 0. From this first grouping, we can say f is equal to 0. If we look at the second grouping, you can see we have something different, where now if y is equal to 0, f is equal to 0, and if y is equal to 1, f is equal to 1. So we can say that f is simply equal to y. And for the third grouping, we have the same thing. So we can say f is equal to y again. Now for the last case, we can see no matter what y is, f will be equal to 1. So we're just going to say f is equal to 1. So let's look back at our multiplexer. And we know if w is equal to 0 and x is equal to 0, we're going to select I0. Now what is I0? Well, no matter what y is, 0 or 1, f is going to be equal to 0. So what we can do is plug a 0 here. Moving on, if we look at the case where w is equal to 0 and x is equal to 1, we're going to select I1. Now what is I1? Now when w and x are both equal to 0 and 1, we found out that f is equal to y. So we can plug the input y into I1. So you can see the trend here based off of each of these groupings. Whatever we determine as f, that's what we'll be plugging into these inputs. So we can complete our multiplexer simply like this. And now we've implemented our original Boolean function using a multiplexer. Now we can move on to our mastery question, which is going to be implementing this function given by all of these sum of products. We're going to do that using a 4x1 multiplexer. So if we take what we learned from the last example, we're going to set w equal to s1 and x equal to s0. This is going to be w and X. Now, because we have a 4 input multiplexer, we're going to divide the truth table into 4. So in our 16 combinations, by setting W and X equal to those selector pins, you can see that for each grouping, W and X are the same values. So now we're left with Y and Z. But we can do a similar procedure, where again we express F as a function of Y and Z now. So in this case, we know that F is going to be equal to 0. Down here, we know that F is going to be equal to Y bar Z bar plus Y Z bar. From this third grouping, we know that F is equal to Y bar Z plus Y Z bar. And for this last grouping, we know that F is equal to 1. So what do we do with this? Well, we know this first input is going to be 0, and the last input is going to be 1. And we can simplify this term. So we can say that F is simply equal to Z bar. So what do we do with this term here? We can't simplify it. And this leaves us to implement this function using everything we've learned so far. So we know we would have two AND gates, and then they would be summed together by an OR gate. And on our inputs, we'd have Y bar Z, and Y Z bar. And this is how we would implement this circuit. So we have a multiplexer and some additional gates. Now, one thing that is different than the decoders is the 4x1 multiplexer symbolizes 4 inputs and 1 output.